Sleepy a bit. Okay. Why? You got a lot of assignment to do. So cool. Haha. Okay. So I try to be quick for the class. Assignment and project, right? Okay. All right. For today class, what we will learn is accelerometer transducer. Okay. For the next lecture, so some of the topic I will skip. Right. It is depending on the topic that will be covered for the test and also for the exam. All right. Accelerometer sensor or accelerometer transducer is actually used to measure the acceleration. Okay, all right. And before we go further about the accelerometer transducer, so let's look about the motion, because the acceleration is quite similar with the motion. Okay. Uh, Motion sensor, or we call it acceleration sensor, right? Accelerometer sensor. It's designed to use to measure the rate of change of position, location, or displacement. Okay, so we can know the displacement and also the location and so on, right? So as we know that from the first derivative of velocity, so we can get it the acceleration. Um, let's say that this is your displacement. Okay, so when you do the first derivative, d over dt, so what you get it here is velocity, right, over time. Okay, and then from the velocity, when you do the derivative also, what you can get is the acceleration. So this one is the basic things lah. Displacement, you can get the velocity, and velocity you can get the acceleration. All right. Okay. And then accelerometer is a primary form of the motion sensor. Okay, and it used to measure the acceleration of an object. So, all right. So this one is the when we derivative the displacement, derivative the velocity. We also can get it back from the acceleration at. All right. Now we can we can integral this one. Okay. Then we can get it is the velocity, right? So of course this one have the one constant. Okay, okay. Normally the constant will be equal to 0 lah. Okay, normally, right? So plus this one, and also from the velocity we can integrate again, right? Integrate again in order to get the displacement. Right? So this is the concept. So when you derivative, so we can get the acceleration. When we integral, so we can get it the displacement again. But the most important thing is the unit, right? So the acceleration is meter per second squared, and then the velocity is meter per second, and the displacement position is the meter. Right. So let's look in terms of theoretical type of motion. So we can have the linear motion, right? So when you throw one object, right, that follow in a straight line, so we call it linear motion. And angular motion is like that move in an arc or circle and so on. And we also have played around with the vibration. So vibration is have something we do with the acceleration. So vibration is mean the phenomenon where the oscillation occur. All right. So we know about the bobble head, for example. So when you push some object, right, some mass, we call it this mass, it into a certain displacement, right? And then when you release it back, so this mesh will turn it back and then go it back and so on, right? So this one we react as the sine wave signal, right? Where you had the amplitude and so on. And from this displacement, you can get the velocity, right? So when you have the displacement and time with the sum of frequency and so on, and then you can have also the acceleration. Okay, right? So this is the vibration. For the shock motion, that's it. Some of the object will suddenly came to the rest, right? For example, you have the ball that you release it, and it will going to be stopped. Okay. Right. So accelerometer principle. What is the basic principle of the accelerometer? Actually, you can do the accelerometer sensor by yourself. Actually, so what you need to have is only you have the mass, right? Any certain mass, and then you connect it into a spring here, and then this one is your base. Okay, so this one is K and this mass. So only you need a two thing, mass and also the spring, right? And this one is will be your reference S naught. So let's look what is the relationship between the acceleration and also the spring, right? The spring. So if you learn about the control engineering subject, so what can you get it here is F equal to MA, right? So and also for the spring, F also the time with the X, Kx. So that's why is K time X, and you can get it MA, right? And then the acceleration, right? In order to get the acceleration is equal to K over M in time with the displacement of X. So X, the delta X, that means X naught, it can moving to the X. So this one we call it is delta X. Okay. So this is the basic relationship between the acceleration and also your spring and also the mass value. Okay. All right. So the mass that we produce an acceleration, we call it is seismic mass. Okay. All right. The part one is a little bit about the theoretical. Okay. And the damping is sometimes we call it this one, right? Have some damping here. So this one will determines your damping, right? The damping coefficient alpha, right? So this is the formula lah. Okay. And then of course when you play around with the vibration, you will have some natural frequency, right? Okay. So when your mass is moved to a certain displacement and then it will return back, so it will have some natural frequency there. So how are we going to use our transducer sensor, right? So how are we going to use to measure the vibration? For example, let's say we want to measure the vibration of the table that move to the x and x axis, right? At the what we call it, the horizontal axis. So you can put your accelerometer sensor, right? You can put it at the table like here, and then on your accelerometer sensor you will have a stop, we call it a stopper there, right? This is the stopper there. So why we need the stopper? Because we don't want our mass that move at the right, move at the left, right? That's mean we don't want to be oscillation is occur, right? Occur. So if so, that's why we put a stop there. Okay, right? So when you put a stump table, right? When you put your sensor, you put a stump table here. Okay, so the acceleration at your sensor is equal to the acceleration on your table. Okay, So that means you can measure the acceleration on the table. Okay, for example, the acceleration on the table is given to you 80 omega squared, right? X naught sine omega t. So from this one, you can find the relationship between the spring of your sensor here, and then also the mass of your sensor here. So what the relationship is given to you, the delta x with time with minus mx over k, and then omega squared x naught sine omega t. Okay, so this is the relationship where you can get it from here. Okay, so 80a is given to you is uh, minus omega squared x naught and sine omega t. So this means k over m here, and then this one the delta x. Right? So this is the relationship. It came from your sensor itself, k and m. Right? Okay. So far, do you have any question? The first part is about theoretical. Okay. Ada soalan? Okay. Clear It's about theoretical lah. Okay. Why we put a stop? Because we don't want to the oscillation occur, right? So that's why we put a stop. So you can put a stop at the certain displacement. For example, you can put displacement to number 2, okay? Maybe at 2 cm, for example, your mass will be going to the maximum 2 cm. And then this is the graph where at the different frequency lah, right? Okay, and then actually because we want to limit the physical side of the oscillator, so it will hit the stop, right? The stopper there, right? Of a rule of thumb, that means our frequency need to be natural frequency is half less than divided by 2.5. Okay, so this is the rule of thumb lah. Alright, so example 14.1 I think is quite simple. So an accelerometer has a seismic mass of 0.05 kg and a spring constant 3.0 times 10 of power 3. So maximum mass displacement is plus minus 0.02 meter before hit the stop. Okay, determine the maximum measurable acceleration in g. Alright, so 1g equal to 9.8 meter per second squared. So first of all, you get the information, and then he want you to find the acceleration. So this is the formula for acceleration between your spring and also the mass, and also some displacement here. So you can calculate k is given, m also is given, and delta x, the maximum is 0.02 on the right. Okay, so you just time by 0.02, and then you can get it in acceleration 1200 meter per second squared. But the question asks you to have the acceleration in g, so you can use the ratio. For example, 1 ratio x equal to 9.8 meter per second, and then ratio with 1200, and then you can get x here. Okay, this one is simple. And then the relationship between natural frequency is given by 1 over 2 pi time with k over m. Okay, so you can get it from the natural frequency here. Okay. Oh, yeah, I skipped this one. So actually the equation for natural frequency is 1 over 2 pi you time with square root k over m here. Okay. When you play around with the accelerometer, you cannot avoid with the natural frequency. Okay. This is the simple example. Okay. Let's look type of accelerometer, transducer. Okay. there are a lot of type of accelerometer transducer right now. So actually, there are in general there are 4 type. Okay, one we call it a potentiometric accelerometer. So during the exam, this type of question will be quite famous lah. Okay, so uh, in this one, you need to be able to draw, for example, the potentiometric accelerometer. So it contain the seismic mass. Okay, any type of the accelerometer will contain the seismic mass. Okay, this is mass, and then is connect to a dashboard here. Dashboard here. Dashboard is like your damper. Okay, and then you will have some spring here. Okay, this is your rigid body, and then you will have a wiper here. This one is wiper here, and then it will have some we call it variable resistor here. Okay, it's like variable resistor here. Okay, and then what is do is when this mesh, maybe you can put it this mesh in certain that you want to measure the vibration. So what happened is when this mesh move it, right? So this one is K, okay? And then you will got it is this wiper also move. And then you got it a set different output here, right? Different output here. So this is the basic accelerometer transducer, potentiometric. But in the exam, you need to be able to explain lah. Alright. So this is the explanation. The seismic mass is connected between the spring and the dashboard, right? Or we call it damper, right? And then the wiper of potentiometer is connected to the mass. Okay, this is the wiper connected to the mass. And then in the presence of acceleration, all right, the displacement of mass is transferred to potentiometer through the wiper. So this one we call it the potentiometer, or sometimes we call it is the variable resistor, potentiometer. Okay, alright. So this one in terms of theoretical lah. So you need to be able to explain. But I think during the exam, yeah, you can open the slide and also you can copy paste, right? Okay, hopefully. Alright, and then the second type is the linear variable displacement transducer accelerometer. So this type of the accelerometer is have also the seismic mass. So I just draw a simple one. Okay, it have two coil here, right? The primary and also the secondary. One and secondary two. Actually, the basic thing is two coil here, primary and secondary. And inside this one, we call it the form, or we call it the hollow. So you will have the movable core, or this one we call it seismic mass. So when the acceleration is equal, so when you move the core, right, to the right and to the left, you will get the different output at here. Okay, so I just draw a simple things lah. Okay, so it contain like you have the spring steel and here, and then it connected to the seismic mass here. And this one, the LVDT, that's mean it contain the primary and also the secondary coil here, right? So what happened when you there is some forces here, some force from here, or we call it maybe we can put it in vibration, right? Happen to here, so it will push your seismic mass, right, to the down and also up. So you will got the different output, right, in terms of the voltage. Is the explanation about it. Okay. Variable reluctance is use the same concept of the LVDT also. So it also contain a few coil here, and then it also have the seismic mass. And also you will have the cantilever beam. Cantilever beam is like your spring steel, right? Macam it's like the small rod like that. And then what happen when you have the several a vibration, right? So that's will push your mass, right, and onto the right and the left and so on. Okay, and you can get it the output from the coil, right? It's the same concept with the FVDT concept. Okay, and then the last one is the piezo accelerometer. So this one is quite famous, the accelerometer sensor that have been used so far. So what is the concept is you will have piezoelectric elements here. So as we know that piezoelectric, when you push or you give some forces to the piezoelectric element, it will generate some voltage there. Okay. So what happened now, on top of the piezoelectric, you put the seismic mass, and then you can put the spring here, right? And then when you push it, right, you give it some forces, right, to the this sensor. It will push the spring, and then spring will push the mass, and mass will push the piezoelectric element, or we call it crystal somewhat, and then you can get it the output, right, from that. Okay, this is the diagram of the piezoelectric accelerometer. Okay. All right. And then the explanation, I think you can describe by yourself lah, and then you can refer this one. If you look at in the Google, you can see a lot of the accelerometer there. So how the concept that is try to measure, for example, like here, right? So this one is use the concept of piezoelectric accelerometer. When you push it, you get some forces, then you can read by using the meter and so on. Okay. All right. So far, do you have any question? So the first part is about theoretical lah. Alright. Do you have any question? Ada apa soalan nak tanya? Or you feel sleepy? Ngantuk lagi? Okay, no soalan. Okay, good. Alright. So that's mean. Ada doktor? Ada. Apa soalannya? Atas. Apa atas? Atas 6.2. Apa tu atas? AM. All this meter used induced current. All the meter used induced current. What is mean induced current? All meter use induced current. So which one that you refer to? This one? This part? Okay, for the I try to answer your question. For this one, this part, okay, for the potential metric accelerometer, that's mean you don't need a supply current or a supply voltage, right? Except the potential meter itself, right? Okay, this one. And then for the FVDT accelerometer, yes, this one you need to supply current, right? Supply sources, right? Here, and then you can read the what we call it the output from here. And same thing with the what we call it variable reluctance from here. So because you use the some coil, right, means you need to inject some current here, right? So that, and then you will get the output from here. For the piezoelectric meter, you don't need a supply current. That means the piezoelectric itself, it will give you we call it output voltage. The good thing about the piezoelectric material, that means when you give some forces into that material, right? We call it a piezoelectric material. It will generate some voltage. It's a good thing about the piezoelectric. Okay. Did I answer your question? The 4 meter. Yep. It's not the meter, it's the accelerometer. Okay. Now it came to the calculation part. Integrated circuit. Okay. Last time we have learned about the signal conditioning. For the accelerometer transducer, there is an signal conditioning that you will use. We call it is integrated circuit. So let me remind back. So what we can get is the acceleration when we integral, right, over dt. Now we can get it the velocity back, and then when we integral the velocity, then we can get the displacement back. So it depends on you. If you want to know about the displacement of your acceleration, right? So we can get it from here by integrate the velocity, right? And now that's mean when you use the integral, that's mean you will use the integral circuit. So all is based from the inverting circuit. So this is your inverting circuit. So still remember back your inverting circuit. This one is the V in and this one is the V out. When we set that the integral, so this one we just replace it with the capacitor. So this one is C, this one is R. Okay. So of course, in terms of theoretical value, how to calculate it, so you can use the Kirchhoff law. So this is a measure of I here. Okay. So this one is IS. IS is always 0. That means there is no current that is from the OM here. Okay. Then you can get it I2 here, and then this one I1 here. So I1 plus I2 plus IS is always equal to 0. And the relationship between V out and V in for integral circuit is given it to you is minus 1 over RC. Now you integral with V in, then I with dt. Okay, so here. So this is the integral circuit. Right. So what is the value of R and C? We will discuss later. Differential circuit, right? Differential circuit is mean you just replace R is here, C at here, and then that's it given it to formula V out equal to minus RC d over dt with V in. So this one, if you want to get it from the displacement, you want to get the velocity you can get the acceleration. Okay. All right. So on what we have discussed before, if you want to get the from the acceleration, you want to get the velocity. That means you need to have one integral circuit. Okay, like it showed to you. So you want to get the velocity. That means you will integral the VA. So that means your input now will be your voltage acceleration. Okay, so you can get the voltage velocity. And if you want to get the displacement, you need to have another integral circuit. So you will get it from the velocity, you will get it the displacement, right? Voltage velocity and also voltage displacement here. All right. So let's look at the example 14.2. 14.2. An accelerometer output is 14 millivolt per G. Okay, design a signal conditioning system that provide a velocity scale at VV equal to 42.9 millivolt per centimeter per second, and also that can provide a displacement signal scale at Vx equal to 0.2 volt per millimeter. Okay, so right now you want to get from the voltage acceleration VA is equal to, I put it equal to 14 millivolt per G, you want to get a VV equal to 42.9 millivolt per centimeter per second. Okay, so this is what you want to get it, right? From VA to VB. That means what you will have here, you will only have one integral, right? One integral. Okay. In this one, your initial idea, right? One integral is your initial idea. So this one C, this one R. Then you got it is your VV. Right? So you only need a one integral. This is your initial idea. Okay. So the most important thing is your unit here. Right? It need to be in terms of the same unit. Okay. So let's do this one. So first step, or what you need to have it is you need to convert from G. Okay. Then you need to convert in terms of meter per second. Right. So make sure that when you got it a centimeter or millimeter, so you need to convert it in terms of the initial the standard unit. Okay, so let's me go through step number 2. Step number 1, you just gather all the information. Now you got it a VA 14 millivolt per G. So now is 1G equal to 9.81 meter per second squared. Alright, so that means your 14 millivolt here, you divided with 9.81 meter per second squared. Now you got it is 1.43 millivolt meter per second squared. So the most important thing is this one, the unit. The unit for acceleration must be meter per second squared. Okay. Alright. Good. Then we are done. Okay. Next step number 3, you just draw your, I call it the integral circuit. Okay, like this one. Alright. Okay. Done. Okay. So now from this one VA here, so we want to get the velocity here. So as we know, I put it step 4. Okay, if we refer to the slide lah, right? So VV is equal to minus 1 over RC. So you integral your VA dt here. So now is 1 over RC here. VA is value is here 1.43 millivolt per meter per second squared dt. Okay, so this is your VV. So what the value that are you going to use is this one, right? It's quite simple, 1 over 1, 1.43 millivolt over meter per second squared dt. So that means your value for R and C is equal to 1. That means your R, you can take it is 1 mega ohm, and C is equal to 1 microfarad. Right? So this one, it make you a simple, right? It will make you a simple thing. So this one, R and C, you just make it equal to 1. And then the value that you can choose for R equal to 1 mega and 1 microfarad here. Now, what you will get it here is minus. So this one, you will integrate. That means this meter per second squared, it will be lost. It will become millivolt. Now is meter per second only. PV. Okay, this is the concept. Alright. So far, do you have any question? Ada apa-apa soalan? Alright. Do you have any question that you're going to ask? No? So what happened is dt, integral dt here, integral. So it will integral this one only. Meter per second, now it become meter per second squared. Now it become meter per second only. Okay? Done. Good. Okay? So that's it, the step number 4. Now, what is the value? Is here. You got it here. Okay. So this is, you check it, is 1 mega ohm, and this one is 1 microfarad, and your VA is now equal to 1.43 millivolt per meter per second squared. Now this one, you got it, is your VB, right, equal to minus 1.43 millivolt per meter per second. Okay, so this one VB. Right. However, we want it 42.9 millivolt per centimeter squared. So that means this value, we need to convert it first. Okay, so now I put it is step 5. Actually, you can just follow to the slide. All right. VB, you got it. VB now is 42.9 millivolt per centimeter per second. Okay. So what we want to do is we want to convert it, this one, all right, to be a meter per second. Okay, to be a standard value, and you can use this one. 1 centimeter equal to 0.01 meter, right? So 1 centimeter divided with 1 centimeter you time with meter per second. Now you got it 0.01 meter second. Okay, this one. So now is VV go to 42.9 millivolt. You divided with centimeter per second. Centimeter per second equal to 0.01 meter per second. Then you got it is 4.29 volt per meter per second. Okay. So we have achieved this standard value. Okay. Alright. So far, do you have any question? Boleh faham kan? Quite easy lah. Okay. So we have convert this one, centimeter per second, we have converted into meter per second. Now, you got it is minus 1.43, then you want to get it 4.29. So what you need to have after this is, remember, so what we need to have here is, we can have the one more inverting amplifier. Okay, then this one you will got it, your VB that you want it is 42.9 4.29 volt per meter per second. Okay, right? Right? So what is this value? This resistor value, what is this value? You're going to divide this one, you divide with this one, right? Then you will get it again here. So let's proceed to the next slide. Okay, all right. So what you need to have that here is we can get it is our G here is equal to 4.29 volt per meter per second. You divided it 1.43 millivolt per meter per second here. So this one we cancel out. Then we got it is here equal to 3000, your gain, and RF divided with R1. This one is your RF divided R1 equal to 3000. Then you can choose, for example, your RF value. Let I choose it 3000K and RF is 1K. Okay, so this value 3000K here, 3000K, this one is 1K, 3000 or 3 mega ohm and 1 kilo ohm. Now you will got it this value. Okay, this value and this value, it gives you the same meaning. Okay, in term of only the different in term of units. Right? This 1 centimeter, this 1 meter. So far, do you have any question? So we have designed the signal conditioning from our input VA here, 40 millivolt per G. Then we can get it 42.9 millivolt per centimeter per second. Okay. Ada apa-apa soalan tak? Is it clear? Yes, clear? Do you have any question? Okay. All right. Okay, good. So we already got it. From the acceleration, we can get it. Can you repeat start from G? Okay. This G, you're going to get the value of RF and R1 here, right? So what is the value of RF and R1 here is depending on your output and input, right? So when you divide the output to input, right, you will got it your G. Okay. Of course, I know that you will ask your G will equal to minus, right? Okay. Right. It doesn't matter. You get it the minus of plus, because your value for resistance will be always positive, right? There is no value for negative. Okay. And in order to get the G, that means the output, you divided the input, you will got the value of G, the gain for your OM, right? And then you got a 3000. Then you can choose for RF value, we can choose in K, 3000K or 3 mega ohm. And then for R1, you can use the 1K. Alright. So why we use the K and K? Because we want to avoid the loading effect. Okay. We don't want that much current will be lost, right, for this one. Okay, clear? Faris, Alani? Okay, good. Yep. The RF assumed for this question or only in test also? It is depending on test, right? So if the test it give it the value for RF and R1, so you can use it. If not, that means you just assume it, right? So that means when RF and R1, so when we divide RF and R1, we should get the same value for the gate. Okay. Right. So now let's proceed. So the next question it asks you to find the VA equal to 14 millivolt per G, and it asks you to get the Vx equal to 0.2 volt per millimeter. Okay. So in order to get the displacement at the between, you should get the velocity. Okay. Now we already got the velocity here. From the first question, we already got the velocity here. Some here. Then this one is 1 microfarad, 1 mega ohm. Done. Then we can get it VV here. This one is equal to 143 millivolt per meter per second squared. Then we can get it minus 1.43 millivolt per meter per second. Okay, is it? Betul tak? Okay, right. Okay, right. So now the next thing is we want to get it VB, we want to get the VX here, right? VB, we want to get the VX here. That means you need to have another integrator here. So let's say this one minus plus going to ground and this one. Okay. So this one your Vx. So you want to get it a 0.2 volt over millimeter here. But of course, the unit of millimeter, you need to convert it in term of meter. Okay, right. So first thing is what you need to do is you need to convert it, this one, to convert it to be meter. So Vx equal to 0.2 volt per millimeter, and we can get it is 1 millimeter equal to 0.001 meter. Now Vx is 0.2 volt divided with 0.001 meter. Then you can get it is 200 volt per meter. Okay, so done. We already converted this one to the standard value meter, and then you can find the value for C and R here, right? Because we use the another integrator C and R here based on that formula. So now you can get it is the Vx here. You integral with Vv dt. Okay. Then you will have the 1 minus 1 over RC here. The Vx here, you got it is 200 volt per meter. 1 over RC, you integral with Vv is here. Millivolt over meter per second dt. Okay. This one 200 volt per meter minus with 1 over RC. So when you integrate, that means you will lose it 1.43 millivolt. So second will be lost. So now it becomes the meter only. Okay. So this is the concept of integration, dt. So this one will be lost. Okay. Now M and N you cancel. That means you want to find the RC value. So RC 1.43 millivolt, you divided with 200 volt here. Okay. Because meter and meter will be cancelled out. So 1.43 millivolt you divided with 200 volt. Then you will got it is 7.15 times 10 power of minus 6. See here. And then you can choose any value of R, okay, that you're going to choose. For example, 751 mega ohm. And then for the C, you can choose is 0.01 picofarad. Okay, so any value that you can choose. So, however, the value for R times with the value of C need to be equal with this value, 7.15 times 10 power of minus 6. Okay, now we already got it, these two value here. So our signal conditioning here is C value is 0.01 picofarad, and this value is 715 mega ohm. Okay, right. So when you choose these two value, you will got it the output that you want, 0.2 over millimeter. Okay, this one. So that means in order to get the displacement, you need to have two integrator here. Okay. Any question? All right. If you forgot it, you can look at back the this one. Okay. Any question? No. Yep. No. No question. Okay. This is the overall circuit, right? Overall circuit that in order you want to get the velocity and also the displacement. All right, guys. All right. The next example is the example that I got it from the exam question, the previous one. So this one, it gives you the accelerometer reading 50 millivolt per G, design a signal conditioning system that can produce an output 0.2 volt per millimeter. So now it wants you to get it from the acceleration to get the displacement. That means you need two integrator here. Integrator 1 plus integrator 2. Okay. And then the first integrator, you can use the value for C and R, 1 microfarad and 1 mega ohm. Just choose a 1 equal to 1. And then first of all, you need to convert G, convert to standard value, and then you can find the VV negative. So I just label it the voltage velocity negative, right? So that we can get it. Oh, this one is we get it the negative value here, right? Then you can get minus 5.096 here. Okay, and then you can find the Vx, right? So that means you need another integrator. However, you need to convert millimeter to convert into the meter value, right? And then you get it to 100 volt per meter here, and then this one 5.096. So this one will be lost, meter per second. This one will be lost. It will be left for meter, right? And then you will divide 5.096. You divide with 200 here, and then you will got the value for R times with C here, and then you can choose any value for R and C here, right? And then you will design your circuit for the accelerometer. Okay. Alright. So far, do you have any question? Ada apa soalan tak? Clear? Clear for accelerometer transducer. Alright, guys. Yep, C. Siti, what is it? Yang C tadi tu, okay. P tu berapa eksponen? P tu berapa eksponen? P pico, right? 10 power of minus 12, eh? Oh, P is micro, right? Oh, actually micro lah, kan? Betul. Micro, P is pico. Pico, that's mean yang mana? Yang soalan ini ke? This one, eh? Okay, let's look. 7.5 M. 10 power of 6, you time with 0.01, you time with 10 power of minus 12. Here, 175 times 10 power of 6, you time with 0.01 times 10 power of 12. Yep, P is pico. This one, P is pico, that means 715 time 10 power of 6. M is power of 6, right? Third. And then P is power of minus 12. We got it, this one. Okay, good. All right, 2 minutes more. Good. All right, this is the example of application lah. All right, I think you can read by yourself lah, this one. Okay, so it can be used in the train and so on to measure the acceleration and so on lah. Okay, and for example, this one, you want to measure the vibration of the what we call this one, the drill. Okay, so you can put the accelerometer here, right? So I think this one you can read by yourself lah. This is only the application. All right, I think that's it for our class for today. So I will send you the video for this topic, right, after this. Okay, guys, thank you for your attendance. I will see you again on next week. All right, but next week I will tell you on what time we will start because I have a workshop on next week. If I can't make the live class, right, so I will send you a video about it, right? So thank you guys, thank you for your attendance. So I will see you again next week, inshallah.